So now there's probably things that people are wondering, and I'm sure at this point now comes the fun questions. People just going, you can't ignore all the analog complexities. What are you doing? Like, where are the passives? You need your resistors and capacitors and inductors. And you'll need to put this in feedback loops. Where are your op amps? You need to have lots of op amps because, operate different frequencies. We use them for all sorts of different things. What's going on here? You're going to have a lot of different types of MOSFETs. You need different ones because you need all of them in saturation. Is that subthreshold or above threshold? Saturation. Above threshold saturation then. Whatever. Okay, now we get to address the artistry of analog design as we start seeing what happens as we talk about this. Artistry? Well, we see that analog design is extremely artistic, and that's kind of part of its sort of charm and wonder at this point. We have one, obviously one person will go, let me start to build my circuit, and they go to their canvas or whatever their tools are, and they draw out, say, their op amp that they need to have for a particular spec. And they're very, it's kind of a neat thing. They kind of very carefully design it. They design all the elements. Another designer comes by, sees the op amp, goes, no, that can be done much better. I know a much better way to do that. They grab their canvas, they start working on it, they build their op amp. And it is also a good op amp. And it turns out both of them are about the same and can have about the same functionality. And yet both of them will swear by whatever one they have in this case. So given that, we need to kind of discuss some of these questions directly. Because, as we start looking at programmable configurable and environment that's on chip, that probably changes the way some of these questions are. And we have lots of questions, as we can still see them. So let's start sort of down a journey and see how this plays out. Interesting journey getting to a bridge. This seems to be kind of a bridge we need to think about. There's going to be a whole bunch of things to crossing over to talking about these kinds of analog design and what are the perspectives in programmable and configurable design. Stop! Who goes there? The one who crosses this bridge must answer 3 questions. Oh, this should be fun. 3 questions basically come along these lines. How do you start to think through subthreshold type design? How do you start talking about programmable design that, is not op-amp centric, is not op-amp feedback centric? And how do you sort of talk about circuit design, the circuit dynamics as your core for filter design, which is more likely what you're going to have in a large configurable system? So how much time do I get? About 10-15 minutes. Okay. So when your typical EC type of engineer thinks about transistor circuits, usually their picture that comes out in their mind is your typical discrete audio amplifier. Now, this typically is what you would have thought it would have been state-of-the-art in like the 70s or 80s, and that would have worked out fairly well. Basically, you're trying to make an amplifier with gain with a bunch of resistors, maybe a capacitor for the input to kind of structure this, and there's some load capacitance. Now, you might also think, okay, there's some op-amp circuits, and that might also work too, but this is pretty normal. And again, this is sort of what would have been state-of-the-art in the 1970s, the 1980s, where you'd have like discrete transistors you pull off to do various analog functions. What we find today, though, is that most of the things we see written in textbooks and most of the sort of core concepts are still all built around these ideas. Where your complex element, the difficult element, is your BJT, or is your transistor. And almost always BJT in discrete case because they're easier to do that. When it's on chip, by the way, the BJTs are much larger than the FETs. Oh yeah, I've got like millions and billions of these FETs on a chip. So that already says something is kind of not connecting here. We know this from digital design. But also on an IC, these resistors are often huge. Typically we're talking like thousands of transistors on that. Now, on an IC, the capacitors are definitely ranges of sizes, so that's okay. Now what happens is when you look at on-chip, you say, well, why don't I try a different approach, like a current source amplifier? Current source amplifier, or anything where I have a current source that's actually setting up the whole structure. Now this is straightforward, because now I can say, well, I can have a couple of these. I could actually build a couple more transistors to kind of deal with the high-pass element with maybe a capacitor. Remember, transistors are really easy to get and really small. So of course we'd try to think about this. And you'd like to get to a point where it's only MOSFET transistors and sort of typical capacitors in a CMOS process, whatever your CMOS process that you're given. There's a whole range of things you could imagine. But your transistors are your current sources, and now we're talking about a current source-based structure. You've got to think about this for a minute. Well, transistors are current sources, you're thinking. What? Well, you take a look at a typical MOSFET, and you might do a typical sort of measurement of this. Maybe you would hold the gate fixed, and then you would actually sweep the drain and actually measure the current. Seems like a pretty typical measurement someone might try to do. What would you end up seeing? Well, in subthreshold or above threshold, but subthreshold is usually where you get a much better current source behavior. What you find is like, wait, it looks relatively flat after you kind of get into the saturation region. It's basically flat. Now, it's not perfect. There's a slight slope in there. And obviously, the gate voltage can change this a little bit. But this looks like, if it was ideally flat, it looks like a current source. It's much closer to a current source than anything else. In fact, if you're not sure, maybe make it a current source and a resistor or a resistive element as a way to start thinking about it. There's more you can do with that. Further, if I look at the gate voltage side, it looks like a voltage-controlled current source. So this is why it's always taught so much in even a linear circuits course, because this is effectively what we're going to need. You're like, great. So I guess it is a current source. And so looking back at the circuit we have, it makes complete sense that we're talking about current sources. But what's interesting is that if you actually start by teaching this from first principles, this is no harder to do than it would have been to talk about resistive loads and other elements. It's no harder to even do laboratory experiments this way. So this works out really well until you realize, okay, now how am I going to set that bias? So let's try to take the next step in this, because we've already talked about, we know about floating gate elements, so let's look at that question. Well, we can now add a floating gate element. Okay, maybe I need two more transistors and a floating gate element to do the biasing. But again, transistors are pretty inexpensive. And you go, well, okay, this is just what we get with one floating gate device, where I can actually get a floating gate element that kind of I can set that current 6 orders of magnitude or more in current based on just programming the charge. So this is like a huge range in, say, frequency responses, which one of the things I'm going to care about it. And I have the current mirror that allows me to do this. That structure then also allows me to do some other neat things too, right? Like deal with any offsets, which is another major problem. And so that can get out the mismatch. And remember, I have like 500,000 floating gate elements on an FPAA fabric. I used one. Of course, I probably used a few more to switch things, but in the end, very efficient way to approach this. And my passives are just not a question. And you kind of notice the analog gets transformed through programmability. We have these sort of transconductance capacitor elements, and we use them all over the place. And we'll get into this in a different frame in a little bit, but what you see is that these structures in general give you sort of the highest bandwidth for the given energy because you're using the dynamics and the physics of the structure. It also typically gives you the lowest noise for a given bias current you could work with. The killer with these structures is always I need programmability, linearity, and offset compensation. Well, we already talked about we can do programmability. This could also be done in a differential pair. Also the offset compensation, we already kind of talked about that's a possibility. By putting the floating gates at the inputs, we could talk about also linearizing it and linearizing exactly what we need to solve the problem. This turns out to be really, really amazing. So when you look at this sort of abstraction, you realize, I can talk about current sources. I can talk about all of these pieces. Well, that allows me to talk about having a whole a very straightforward model in subthreshold for all these pieces where that sigma comes directly from the slope. And the source in this case for these measurements was at ground, but this could always be used in a different way. Here's a neat thing. Once I look at this structure, what happens? Well, I'll just kind of move things around and take a log of it. I realize I have a term that's roughly constant. It does change potentially a little bit over current depending on temperature, like proportional to temperature, depending on things. Longer discussion there. But then I get a place that's linear, between all of the terminals, and kappa and sigma are relatively temperature independent. This is very interesting for analog design and allows you to abstract it. And in fact, the fact that it exists has allowed us to actually get around away with using linearized models in so many cases when in some ways we have almost no right for it to work. So the core of that says, well, wait, I have that core idea and sort of changes between them. And that gives me 4 options because I can't use the gate as an output because it has no current. That gives me then 4 possibilities for inputs and outputs. And I could actually just start looking at the circuits, and it's pretty interesting and pretty straightforward. Where 1, I could look at the source follower element, and I could just look at its parameters and its properties. I could look at a common source element, which, so for the common drain one, most people might believe that, yeah, that probably, I could see that being linear. The common source one, you solve the same way, and it's still large signal linear. And it gives you quantities you, by the way, would have solved for had you done a small signal analysis. And you could talk about the first common gain case, which is actually sort of a high gain amplifier case, but then you can also do the reverse case, which is often thought about for cascodes or for voltage regulators, which gives you the low gain case. And this kind of gives you a way to just abstract this whole piece out right off the bat. And this is basically what you get for one transistor circuits with current sources. And yeah, if you don't have a good current source and you have to use a resistor, okay, fine, you could do that. But this is kind of the fundamental pieces that you begin with. And floating gates get used everywhere and can set the bias and the bandwidth and all the other good parameters. So then you could say, well, wait, I got op-amp design questions too. And I'm like, all right, well, one of the first things you find is that with floating gate elements, you don't really need the feedback to get accuracy. That's usually why you do it. You usually don't want something that has a gain of 100,000 in open loop. Unless you're making a comparator, that's a different discussion. So this becomes sort of, one of many fundamental blocks, not the fundamental block, and you really start to find things get much more simplified there. But what's interesting is that the core topologies are actually fairly straightforward, because you can talk about a 2-stage amplifier, which you see in every textbook, mostly because it's a hard problem. You also see a folded cascode and a transconductance amplifier. Here's what's interesting. If you look at the parameters in all 3 cases, you get very similar parameters in any of them. And so it's really a question of artistic design which you'd want to do. Probably the transconductance amplifier and the folded cascode are in general easier ones to design, easier ones to sort of replicate and do in many places, with the fewest amount of parasitic craziness that can happen. But you can get away with only probably a couple different topologies, and that's sufficient for a fully configurable structure, particularly with a programmable bias current. And you think, okay, this is getting interesting. But here's what happens is that once I can start having a programmable bias current, that changes the way I do filters, and I want to do them with dynamics. In many cases, I'm not necessarily requiring op amps. Well, let's kind of look at how I might think about it. Well, normally I just want to do a first order low pass filter. A simple R and a C will do that, so why not use the dynamics? Why not use the dynamics of other kinds of larger circuits? Well, you can start talking about different approaches, right? And the classic approach is just take, feedback around an amplifier. If you're doing it on chip, you're probably using transistors like the classic sort of 4-transistor linearized resistor element that originally came out of Yanusovitis' group, and other people worked on this. But there's your resistors, and you can build some really nice structures out of it. And the things are related to those particular devices. One of the preferred approaches for high linearity is often, which is what you'd want for good SNR, is to actually do things like use the early effect on these structures. But here's the thing, that op-amp still needs to be included in all of these issues, because that op-amp is usually just kind of like, oh, it doesn't matter, but it turns out to be everything that sets all of these criteria. I could do switch caps, which is a wonderful approach, but it usually means I've got to oversample to look like an analog structure, or I have to think about this in discrete time. All of that continuous time stuff just kind of went away as soon as we used this. And it has amazing linear range. You can get almost full rail-to-rail linearity. You can control it with frequency, which is nice. If you're scared of floating gates, it's one way to approach it. But it still turns out that op-amp matters all the way through the structures. Or I can talk about these transconductance capacitor elements, and things look pretty effective and efficient. Oh, and the floating gates immediately program these structures. So there's some pretty neat things you can do here. And, again, all of this is enabled with the floating gates. Without that, this really doesn't go anywhere, and that turns out to be important. And so this really changes it, where things are now transistor-centric design. You're going to, maybe only needing a couple or maybe no passives for, in practical sense. There always probably are a couple in biasing the structure. Things are subthreshold centric design, which gives you the wide tuning range. It also tends out to be really important for scalability, because subthreshold always shows up, above threshold disappears as you scale to more and more advanced processes. Everything is built on floating gate current sources, so you have that, sets your bandwidth, your biases, the noise. You get exactly what you want over 6, 7, 8 orders of magnitude. It's incredible what you can do there. The floating gate elements also, allow you to have inputs in linear range and offsets. As a result of that, you can really talk about abstracting things because of the programmable transistor circuits. You actually have all of these interesting amplifier concepts and approaches that really come out about this. And the thing is, we don't need to get accuracy by feedback. You get accuracy from programming. You get accuracy in many different ways. And then the filter approaches really allow us to focus on things that use the dynamics and are utilized as efficient computation as possible throughout the entire sort of spaces that you'd want to work from. All in an FPAA framework. And strange enough, this answers those 3 questions. Fine, off you go. Thank you very much. And we go across the bridge.